So, welcome student to the new class of introduction of nonlinear optics and its application. So, today we have lecture number 51. So, in the previous lecture we discussed about four-way mixing and generation of cross phase cross talk frequencies, how the cross talk frequencies can be generated with making some phase matching condition which is delta k is equal to 0. So, today we will learn more about the four-way mixing because this is a fascinating process and how this process is used to amplify a signal that we will going to learn today. So, today our topic will be parametric amplification under four-way mixing. So, parametric amplification means we launch the parametric amplification process we have already learned in the second order effect, where we launch a light and another signal is there and we call this light is a pump light, and because of this nonlinear interaction what happened, there is an increment of this signal. Also another wave is generating which is called the idler wave, and this was entirely a chi2 effect, that means the second order effect. So, only two waves are mixed there to generate the third one or amplify one of them. Today we will going to learn a similar kind of process, but instead of having two wave we have interaction instead of having the second order interaction we have the third order interaction. So, the interaction will be now not restricted with the two wave, we will have three wave. However, this three wave not necessarily be distinct to each other. If two waves are launched, then there will be mixing of these two wave in such a way that one wave can come twice and we will generate a four-way mixing kind of stuff. So, let us try to find out what we try to say here. In four-way mixing there are different kind of categories because the generation of the frequencies are large. So, this is a typical example of some frequency generation. So, what is happening here? I am launching three fields with frequency omega 1, omega 2 and omega 3 as shown in here. Chi 2 is not equal to 0, that means we should have a nonlinear interaction between these frequencies. This nonlinear interaction will be of the order 3. So, E cube term will be associated with that. So, when cube term is associated with that, so we will have the combination of frequencies. So, this is a very specific combination, the sum, simply the sum of all frequencies, whatever the frequencies we launch, we should have a fourth frequency omega 4 which is sum of omega 1, omega 2 and omega 3. You should always remember that omega 4 in general can be generated in this many ways, plus minus of omega 1, plus minus of omega 2, plus minus of omega 3. So, these are the numbers, there are huge numbers. I think this is a 8 different combination you can consider, and omega 4 can be generated with 8 different configuration if we consider omega 1, omega 2, omega 3 are distinct. So, among these 8 configuration or frequencies, we choose a particular frequencies which is just omega 1 plus omega 2 plus omega 3, which is this one. If I want to generate a frequency omega 4 which is sum of all the frequencies under this four-way mixing process, then the corresponding energy diagram will be simply like this. So, omega 1, omega 2, omega 3, these are the three frequencies that will merge each other and generate a omega 4 frequencies. The energy conservation is H cross omega 1, omega 2, omega 3 with a plus sign. So, H cross omega 1 plus H cross omega 2 plus H cross omega 3 is simply equals to H cross omega 4, which is this equation. This is the energy conservation. But at the same time, if I consider the momentum conservation, then I can write that K1, K2 and K3 are the propagation constant or the wave vectors of the photon with frequency omega 1, omega 2 and omega 3, and they will sum up and generate another photon with a frequency omega 4 whose wave vector is moving in k4 direction. So, this momentum conservation figure suggests that the phase matching may not be collinear. So, this is a non-collinear kind of phase matching that is possible, or normally this is the case. As far as the equations are concerned, so we already solved this equation in the previous class. This is the starting equation, that means the nonlinear Maxwell's equation. So, this nonlinear Maxwell's equation, we have a source term, the procedure is exactly identical that we have been using. From that we now put E, and when I put E omega and P NL omega, I will have evolution equations of this. So, P nonlinear omega will contain omega 4 frequency. So, that is why E1, E2, E3 will be here, and eventually we will be having differential equation for 4 fields E1, E2, E3 and E4. E4 is more important, and in E4 I find that it is associated with E1, E2, E3. So, these are the source terms. So, these are the coupled equation. So, if I want to solve this coupled equation, we need to check that how this equation can be solved. It will be not that easy, but in principle we can solve this coupled equation numerically and find out how this field will be evolving. Now, we will go to the next thing, which is parametric amplification. So, sum frequency generation is one kind of four-way mixing, but parametric amplification is quite interesting, where omega 1 and omega 2 are launched, and we are getting omega 4 and omega 3 at the output. So, we are launching two frequencies omega 1 and omega 2, and we are getting omega 3 and omega 4. So, here the energy relation is, or the energy diagram is something like this: omega 1 and omega 2 are merged to generate omega 3 and omega 4. So, this is the energy conservation equation. Similarly, in the momentum conservation equation is also like something. So, momentum conservation equation suggests k1 plus k2 has to be equal to k4 plus k3. So, this is the figure of momentum conservation. Now, I want to find out in parametric amplification how this omega 4 and omega 3 will going to evolve. And the concept is, if I now launch something here, small signal omega 3, this omega 3 will be amplified because omega 3 will be generated inside this under 4-way mixing, this parametric process. Also omega 4 can be evolved. So, I can amplify certain signal having frequency omega 3 and omega 4. So, let us try to find out how the field equations one can generate, which is again the similar process. The starting point is to define our electric field of E1, E2, E3 and E4, where E1, E2, E3, E4 are the corresponding frequencies, the field of the corresponding frequencies omega 1, omega 2, omega 3 and omega 4. So, these 4 fields are now combined together to generate the total electric field ET. So, total electric field ET is now P nonlinear, related to P nonlinear, and this P nonlinear is epsilon 0 chi 3 and total electric field cube. So, when I make the total electric field cube, so omega 1, omega 2, omega 3 and omega 4 will combine, because I am making a cube of that, and as a result we will going to generate different kind of frequencies. But our aim here is to find out the frequencies omega 3 and omega 4. So, if I do, then quite easily I can say omega 3 is omega 1 plus omega 2 minus omega 4, and omega 4 is omega 1 plus omega 2 minus of omega 3. The structure is again some sort of these crosstalk frequencies, that omega 1 plus omega 2 minus omega 3, or omega I plus omega j minus omega k, where I, j, k are not same. So, next let us see how these things. So, P nonlinear will be epsilon 0 chi 3 E t whole cube. Et is the total electric field, as I mentioned, it is E omega 1, omega 2, omega 3, omega 4 whole cube, and now I try to find out only the corresponding frequency omega 1. So, omega 1, if I want to find out how this omega 1 can be there, so omega 1 is omega 3 plus omega 4 minus omega 2. So, that means in P nonlinear term, this frequency component omega 3, omega 4 are plus, that means I should have electric field E 3, E 4 multiplied, and omega 2 minus, that means I will have E 2 star. So, this should be the structure of the electric field in P nonlinear term, and here this is the thing. Since these three fields are distinct, so we will have a 6th term as a degeneracy factor. So, this 6 is sitting here. We are making cube of this whole field. So, according to our definition, it was a half of that. So, 1 by 8 term will come because I am making a cube of that thing. Exponential term should be there also. So, exponential term, since I am talking about omega 1, it is omega 3, omega 4 minus omega 2. So, k 1 should be k 3 plus k 4 minus k 2. So, here it is written, which is a key component, the phase term, and omega 1 will be there because I am generating the frequency omega 1 here. So, my P nonlinear term is ready. Once my P nonlinear terms is ready and total electric field, the expression of the total electric field is ready, I can use again my nonlinear Maxwell's equation. When I use the nonlinear Maxwell's equation, I readily find out what is the field equation, and the field equation is simply 2 I k E I z minus 6 by 4 mu 0 epsilon 0 omega 1 square chi 3, the entire term, where delta k is the corresponding difference of the corresponding k 1 plus k 3 minus k 1 minus k 2. This is the difference between the propagation constants. So, if I simplify, it should be like this. I believe now so many times we are deriving the electric fields of different frequencies. So, you are now quite familiar with the procedure. So, you can apply the same procedure for other three fields, and you can generate the evolution of all the fields. So, these are the evolution equation or the governing equation of all the fields under 4-way mixing. Only thing is that here it is E 3, E 4, E 2 star. For 2 it should be E 3, E 4, E 1 star. You just remember that all the cases you need to find out the correct frequencies. So, here the frequency component is omega 2. So, how you get the omega 2? You will get omega 2 as omega 3 plus omega 4 minus omega 1. So, that is why it is a star. In the similar logic, you will get omega 3, the field of omega 3 and the field associated with omega 4. Once we have this 4 equation in our hand, then the next thing that from this 4 equation we can derive the Mandeley-Roux relation. So, this Mandeley-Roux relation is nothing but some sort of energy conservation. So, all the 4 equations are coupled to each other. If you look carefully, they are coupled to each other. That means the energy E1, E2, E3, E4, they are evolving. They are evolving in such a way that there is a interrelationship between these things. So, this is a source term. In the source term, they are coupled. So, some sort of energy exchange is always there in between, and that is the case because if you look that omega 1 and omega 2 is generating omega 3 and omega 4, that means obviously some kind of energy distribution is there, energy exchange is there. Now, the question is the total energy for this case will remain conserved or what kind of things we have. So, in order to do these things, we need to calculate the total electric intensity. So, this total electric intensity is something like half epsilon 0 n1 C E1 mod of E1 square, which is the total intensity of electric field E1. So, now d I1 dz is equal to half of these things whatever we have as a constant and the corresponding derivative. So, the derivative with respect to z gives you this quantity. Now, d E1 dz is known from the previous slide. If you look, so d E1 dz is here, it is here. So, this I will use in the next slide, and if I multiply this d E1 dz with E1, so I will have E1, E3, E4 with a star, E2 and the corresponding, because this is a star of that. So, we have a complex conjugate. Once we have a complex conjugate, I should have I as minus I. So, that is why this minus term is there and I take common outside. For the next term, I will have a similar kind of things, but it is again a complex conjugate of the first term. So, I should have E1 star, E4, E4, E2 star, e to the power I delta k z. From here also we can see few things, that N1 C and N1 C will cancel out, and eventually we have half epsilon 0, which is a constant, chi 3 is a constant, and omega 1 is again a constant, but I want to write this omega 1 here in the left hand side, like 1 by omega 1 d I1 dz is this term. Now, here you can see this term is really a constant, even it is not depending on omega 1, omega 2, omega 3 or n1, n2, n3. This should be same for all the terms. Inside the bracket we have something here. Now, we will do the same thing for E2, E3 and E4. If we do these things for E3, E4, E2 and E4, you will going to get a similar kind of expression here for I2. So, that means these two are identical expression, but once we have I3 and I4, you will again have a similar expression, but with a negative sign. So, this term will become positive and this term will become negative. Again d I dz I d omega 4 will have, we will have the same thing, but only thing is this term will be positive and this term will be negative. So, from this 4 expression we can write a general thing, and which is 1 by omega 1 d I dz is equal to 1 by omega 2 d 2 dz is equal to 1 by omega 3 d I dz with a negative term and 1 by omega 4 d I 4 dz. So, this is basically, this relation is the Mann-Leroy relation. This relation we have already figured out in our second order effects, when we generate some frequency generation or difference frequency generation or other parametric generation. This is always valid. In terms of photon number, I can say that delta n1 is the photon number, the change of photon for omega 1 frequency, the change of number of photon for omega 2 frequency, it is same, because omega 1 and omega 2 are combining to generate omega 3 and omega 4. So, that is why the change of omega 1 photon is equal to the negative change. So, that means if I write a minus sign here, so omega 1 and omega 2 photon are collapsing to generate the equal number of omega 3 and omega 4 photon. So, this basically the physical significance of the Mann-Leroy relation, and we will readily get this expression starting from our old Maxwell's equation or nonlinear Maxwell's equation. Just evolve the field equation, and from this field equation we can find this expression. Well, next we will go further. We will try to study the parametric amplification under 4-way mixing in optical fibers. So, what in optical fibers we do? So far we have a knowledge that how 4-way mixing can generating different frequencies. It is not generating different frequencies, it is also generating some frequencies and which can be amplified. So, this can be used as an amplifier. So, using this concept, now we try to apply this in fiber optics, where we launch, this is the schematic diagram of what is going on here. So, we launch a very strong pump here omega p and very weak signal, and in the output we are going to generate omega I, which is idler, and omega p, which is there because I am launching very strong signal, very strong pump, and here the signal is amplified. So, we have an amplification of this signal, that is important. So, I launch a very small amount of signal in the output, with that we launch a very strong pump. The strong pump will be there, omega I will generate as idler frequencies and omega s will generate, and it will rather amplified because I have some amount of omega s at the input z equal to 0 point. Now, if I write the energy equation in the previous case, which was a degenerate kind of amplification. So, non-degenerate amplification, the previous slide if I go. So, we were generating the frequencies omega 1, omega 2 and then generating omega 3, omega 4. Now, if omega 1, omega 2 are same, which is the case, we called it this omega 1, omega 2 same thing as omega pump. So, this energy diagram will slightly change, omega p and omega p 2 omega p photon will combine, and as a result it will going to generate omega I and omega s, two different frequencies. So, in the previous notation it was something like omega 1 plus omega 2 is equal to omega 3 plus omega 4. Now, I just modify this, I say change the name, omega 1 is omega 2, which is omega p, omega 3 is suppose omega s, and omega 4 is the idler frequency omega I. If I replace these things, so I will have an expression like this, this is the energy expression. So, energy conservation expression. So, now we have three fields omega I, omega s and omega p. Omega p is half E p e to the power I k p z minus omega p t plus complex conjugate, omega s is half E I e to the power I k s z minus omega z, and similarly for omega I. Again, p nonlinear should be the combination of these three fields, because inside we have these three fields, cube of that epsilon 0 chi 3 and E cube, where E is the total field. So, I make a cube of that. So, that means there will be a combination of omega p, omega s and omega I will be there, but which frequency I will consider? I will consider omega s. So, if I consider omega s, then omega s should be 2 omega p minus omega I. This is the component, this is the frequency component we will concern about. So, this is the structure, energy diagrams are there. The next thing is to find out what is my p nonlinear. So, p nonlinear will be combination of all these frequencies. In optical fiber, what happened? I need to find out my p nonlinear. This is important, and we should be careful enough to find out how these p nonlinear terms are there. So, p nonlinear omega p, that means how the electric field of E p will experience the thing. If I write, I just write this way, it is 3 E p square E p e to the power k p z minus omega t. So, there will be many terms. So, omega p term can be generated in another way also, but I only take the cell phase modulation term because pump is very strong. So, since pump is very strong, we can consider pump as a constant. So, since it is a constant, I am not going to take any other source term as p nonlinear, and I just consider only the cell phase modulation term. Once I express the cell phase modulation term in this way, for other two cases, which is a small signal omega s and generated idler, I will have 1 by 8 epsilon 0 chi 3 as usual, and inside that we have two term. One is the cross phase modulation and another is the 4-way mixing. This 4-way mixing term we have discussed earlier several times. So, I am not going to discuss this again. So, you know that if I want to generate omega s, it will be 2 of omega p minus omega I. So, my corresponding electric field will be E p square, which generate 2 omega multiplied by E I star. Exactly, if you look here, so E p star, E p square E I star is there. The corresponding electric, the corresponding exponential term with the field propagation constant is also written here, and the degeneracy factor 3 is coming because two distinct, there are not 3 distinct field, rather 2 fields are distinct, but E p and E p are same because I am multiplying twice. So, that is why the degeneracy factor should be 3. But another term should also be considered here, which also give rise to omega s frequency, and that is the E p star. So, we will have a combination E p star and E s. E p star, basically this is omega p, this is minus omega p, and this is omega s. So, I will have this term also. And another term, the cell phase modulation and cross phase modulation for other two is also possible if I write very carefully. So, that means E I star E s also give rise to a frequency omega s, and another term E s star E s also give rise to a same frequency. So, this is a cross phase modulation with E I, this is a cell phase modulation with E s, this is a cross phase modulation with E p. So, E p will be more important because pump is very high. So, that is why only I took this term here and the corresponding 4-way mixing cases term, which is this. So, these are the two terms, you should be very careful, there will be many terms, but which term I am taking here? I am taking only the cross phase modulation term with respect to E p because E p is strong field. So, this effect will be much stronger than the cross phase modulation of E I, which is a weak field, or the cell phase modulation of E s, which is also very small, we can neglect that, and the corresponding 4-way mixing where E p is associated with that because E p is strong. So, all the field, strong field related to E p will be considered in P nonlinear, which is a source term. In the similar way, P nonlinear omega I is also a source term, and we can also generate or write this expression for P nonlinear omega. So, here I should stop my class because so far we are deriving the equation for the signal amplification. So, for signal amplification we derive the source term. There will be 3 different source term, one is for omega p, another for omega s, and another for omega L. Eventually, we will going to use the source term for omega s, but how these source terms are generated is important to note, and that is why I in detail I try to make you understand how these different field combinations should be there in the source term. So, with this note, let me conclude here and see you in the next class. Thank you for your attention.